Hi everyone, here's chapter 20, and in this chapter we're going to learn about the chemistry of carbohydrates. So carbohydrates, they are basically polyhydroxyaldehydes or polyhydroxy ketones. You can see these two drawn molecules. There are lots of hydroxyl groups. So they are polyhydroxy, could be an aldehyde, so this ends in aldehyde, or it could be a ketone. Okay. These are two Fisher projection formulas for D-glucose and D-fructose. So D-glucose is a polyhydroxyaldehyde. It's an aldehyde, and D-fructose is a polyhydroxy ketone. The structures of glucose and fructose differ only at the top two carbons, but the rest are the same. You see at the bottom you have a CH2OH. OH on the same side, these two, and then OH on this side, same, but these two, the top two carbons, this is an aldehyde and alcohol, this is an alcohol and a ketone. That's the only difference in glucose and fructose. How do you synthesize these carbohydrates? Basically, plants does it with carbon dioxide and water in the presence of sun's energy. The process of photosynthesis produces glucose and oxygen. Glucose and oxygen in the process of oxidation gives us carbon dioxide, water and energy for us to function. Glucose is the most abundant carbohydrate in nature because that is the most stable one, and you will see why it is as we go along this chapter. Carbohydrates could be simple carbohydrates. We call them as monosaccharides. Those are single sugars. Or it could be complex carbohydrates as disaccharides, meaning two sugars hooked together. Oligosaccharides when there are 3 to 10 sugars hooked together. Polysaccharides would be when you have more than 10 sugars hooked together. So a polysaccharide is made up of monosaccharide subunits. By hydrolyzing a polysaccharide, we can get the monosaccharides. The smallest aldose means any sugar ends in ose. Okay, aldose means since it ends with an aldehyde. So this is the smallest aldose, which is the glyceraldehyde. So the glyceraldehyde is the smallest aldose and only one whose name does not end in ose. The rest will be ends in ose. Okay. So this is a glyceraldehyde. It also has an asymmetric center, meaning there are 4 groups or atoms attached to carbon, 4 different groups. This has a OH group, it has a hydrogen, it has a CH2OH group, and it also has this aldehyde group. So it is an asymmetric center. Now these are the enantiomers of glyceraldehyde. So you remember enantiomers are the RNase configurations of the molecule. When you draw the molecule representing with the wedges and then the dash, it will tell you how the bonds are located around the carbon atom. This OH group, this line and this represent the bonds. These two are on the same plane as the plane of this slide. Okay, and this hydrogen represent with the dashes that it is away from us, and CH2OH group is coming towards us, which represent it's coming towards us. So when you find out your RNase configuration, we want to make sure the smallest group, the smallest priority group should be away from us, and we give the numbers excuse me, giving the highest priority based on the atomic mass. So oxygen gets the number 1 priority, and then this carbon. Though there are 2 carbons, we give this carbon priority because it has a double bonded oxygen. We can consider this carbon has like 2 oxygen atoms and hydrogen, whereas this carbon has 2 hydrogen atoms and an oxygen. So this gets the next priority, and this carbon gets the 3rd priority. So when you number them 1, 2, 3, they go in the clockwise direction, and we say this is your R configuration. And then the way that this is drawn, this is the mirror image of the R configuration. So hydrogen is here, CH2OH group here, OH here, and then aldehyde group is right there. So if you number them, this gets a number 1, priority 1, 2, 3. It goes in the counterclockwise direction, that is the S configuration. And this plus and minus represent, now one of the characteristic of the enantiomers are when you put them in front of a plane polarized light, they rotate the light. Okay, so the way they rotate, so one enantiomer would rotate it to positive direction, the other one would rotate into negative direction. So based on how it rotates the plane of the plane polarized light, that's what this plus and minus represent. That is nothing to do with the RNS configuration. So you can find out the RNS based on the priority groups, and then how it rotates the light gives us the plus and minus designation. Okay, and this is the perspective formula. We can put it into Fisher projection. Okay, so the Fisher projection, the way it is drawn, so these horizontal lines represent as the bonds coming towards us, like the wedges, like this. So this represent bonds are coming towards us, this OH group and hydrogen. This vertical line represent as if the bonds are away from us, like the dash bonds. Okay, so hydrogen is coming towards us. Remember, we need to get the configuration putting hydrogen to the back. So the way it is drawn, we can find out how the numbering goes. So the oxygen would be number 1, this would be 2, this would be 3. So the way it is drawn, it is going in counterclockwise, but the hydrogen is coming towards us. Since it's coming towards us, the way the Fisher projection is drawn, we always have to get the opposite of what we get the way it is drawn. So since it's going in the counterclockwise, hydrogen coming towards us, but we want hydrogen to be away from us, so that will make it R configuration. Hydrogen is on a horizontal bond, so counterclockwise is R. So this is R glyceraldehyde, and again, so this hydrogen is again coming towards us. So this is number 1, 2, 3. It gives us the R configuration. But if you take the opposite of R, since hydrogen is coming towards us, we want to make it away from us, so that's going to be S. Okay, so these are the Fisher configurations for the glyceraldehyde, R and S. D sugars and L sugars. And we give another designation to these sugars based on where the hydroxyl group locate in the Fisher projection. And that hydroxyl group is the very first asymmetric carbon. Now this CH2OH, so this is the last carbon. We are not considering the very last carbon, the one before that. Okay, so if the hydroxyl group locate to the right, we call that as a D sugar, D glyceraldehyde. OH group is on the right, and then the L glyceraldehyde is going to be a mirror image of the D glyceraldehyde. So now you can see OH is to the left, which is L glyceraldehyde. You can remember this. L mean the hydroxyl group is to the left if we only have D and L, and then the D is the other one when it is to the right. Okay, and it is the same thing here. Now this is another sugar, D-galactose. Remember, we are not looking at the hydroxyl group on the very last carbon, the one before that. OH to the right, so that is a D-galactose. OH to the left, that is L-galactose, mirror image of the D-galactose. So the L sugar is the mirror image of D sugar. And this D and L, they are not related to plus and minus. again. Okay, so this is D plus glyceraldehyde. D and L indicate configuration. Plus and minus indicate how the compound rotates the plane of polarization of plane polarized light. If it rotates clockwise direction, there would be positive. Counterclockwise, there would be negative. That has nothing to do with D and L configuration. Now this is D-glyceraldehyde molecule. Now if this carbonyl group is oxidized, this would become lactic acid. But this would rotate into positive direction, this would rotate into negative direction, but both of them are D sugars because the OH group is to the right. Okay. And then these are called aldotetroses. Again, now you know aldo means aldehydes. Tetroses mean 4 carbons. So this one, 1, 2, 3, 4, this sugar is D-erythrose. And now the mirror image of that, this is L-erythrose. So they are enantiomers. Now for the D-erythrose, you can keep this OH on the right side. You can change the hydroxyl group and hydrogen. So this one, that will give you a different sugar. This is D-triose. Still it is D because this hydroxyl group is to the right. And the mirror image of that would be L-triose. So these two are enantiomers. These two are enantiomers. And these two are diastereomers. This and these two are diastereomers. Okay. Aldotetroses have 2 asymmetric centers and 4 stereoisomers. Now you can see the configuration of the D-aldoses. Now you see here you can have for any D sugar, you can also have L sugar as well. D sugar, L sugar. But here we are only looking at the D sugars starting from D-glyceraldehyde. D-glyceraldehyde, so the penultimate hydrocarbon has the hydroxyl group to the right. Okay, and this has 1, 2, 3 carbons. So you add one more carbon to this molecule. Okay, so you're going to be adding a carbon between this carbon and this carbon, 1 and 2 carbons. You keep the bottom like this is CH2OH, OH, and then you put the OH group to the right. 1, 2, 3, 4. So this is D-erythrose. Okay, and remember we are only looking at the D-erythrose. But for the D-erythrose, you can have one sugar with this OH group to the right. But then you can also draw the enantiomer for this one. Not the enantiomer, diastereomer. So keeping the OH here, the penultimate OH, but you only change this OH group, carbon OH, these two switch. It comes to this side. That's also a D sugar because the penultimate carbon has the OH group to the right, but this is D-triose. Now for the D-erythrose, you can add one more carbon and a hydroxyl group. One goes to the right, one goes to the left. Now this has 5 carbons, so this is called D-ribose, this is D-arabinose. Similarly, you can add another carbon between the carbonyl carbon and this carbon with hydrogen and OH. OH can go to the right, OH can go to the left. This is called D-xylose and this is D-lixose. Okay. And then if you add one more carbon to these 5 carbon sugars, that's going to be at between this carbonyl carbon and this carbon. If it goes to the right, OH group goes to the right, that is D-allose. OH group goes to the left, that is D-altrose. And from the D-arabinose, you can add a OH group to the right, hydrogen to the left, that is D-glucose. And then the OH group to the left, and then the hydrogen to the right, that is D-mannose. Okay, and then from this D-xylose you add one more carbon with hydroxyl and hydrogen. Hydroxyl to the right, D-glucose. Hydroxyl to the left, D-iodose. And for the D-lixose, OH to the right, D-galactose. OH to the left, D-talose. Interesting. A little bit complicated, right? Yeah, but you got the idea, main idea. Okay, excuse me. Now you saw that most of these carbon or the glucose or the sugars will change their configuration at a certain carbon atom because we are only changing sometimes one hydroxyl group. Okay, so we call them as epimers. Epimers define configuration at one asymmetric center. Now this is D-ribose. Look at the D-ribose and D-arabinose. CH2OH, CH2OH. So D, OH to the right, OH to the right, OH to the right, OH to the right. And then for the D-ribose, your OH is also to the right. Arabinose, that is OH to the left. So ribose and arabinose differ only at carbon 2. So this is carbon number 1 because the carbonyl group gets the priority 1, 2. Carbon will get the priority 1, 2. So we call them as C2 epimers. So the ribose and the arabinose are carbon 2 epimers, meaning their hydroxyl group change at the carbon 2. And between iodose and talose, they are 1, 2, 3. They are C3 epimers. Similarly, D-mannose is a C2 epimer of D-glucose. Mannose. This is mannose and this is glucose. Everything is same except the carbon 2. So this is right, this is left. So they are C2 epimers. Okay. We don't call them enantiomers, but we call them as epimers. Not the diastereomers either, but epimers. And then the D-galactose is a C4 epimer of D-glucose. D-galactose here. 1, 2, 3, 4. OH group is to the left. 1, 2, 3, 4. OH group is to the right. So the glucose, D-glucose and D-galactose only differ at the carbon 4. So we call them as C4 epimers. Okay. So how does the epimerization takes place? Now this is the mechanism. This happens in the presence of a base. So this is D-glucose. Remember we said glucose and mannose, they are C2 epimers. So now this is glucose molecule. You have a carbonyl group, you have a OH to the right. So the base always gets the hydrogen next to the carbonyl group. Remember we call this as an alpha carbon. Alpha carbon is more acidic. We learned about that. So when the base comes in, it grabs the alpha carbon, hydrogen, and forms an enol. Remember enol? So it gives us the pi bond here, carbon-oxygen pi bond breaks, and the electron goes to the oxygen. So now you have an enolate ion. Now once the enolate ion happens, enol can go back to the ketone. When it goes back to the ketone, now this is a sp2 carbon right here now. So oxygen carbon can reform the pi bond, and then this pi bond can go and grab a hydrogen. When it grab a hydrogen, so this sp2 carbon is going to become sp3 carbon. Trigonal plane arrangement will become a tetrahedral arrangement. So it can have the two possibilities. Okay, so when the hydrogen attached to this carbon, you can have the OH group as it is and hydrogen can go to the other side, or you can also have the opposite one. So the hydrogen can go to the other side and OH can be to this side. So if that epimerization takes place, so you can have a mixture of D-mannose and D-glucose. Okay, so this equilibrium can take place going back and forth. So the D-glucose epimerized to become D-mannose through this process. Okay, it is a reversible process. Enediol rearrangement. Now you can see here how a glucose, which is a aldose, can become a ketose through this mechanism. diol rearrangement. So D-glucose, and this is also happens in the presence of a base. So hydrogen most acidic takes this and form the enolate anion. Once the enolate anion forms, so this enolate can grab a hydrogen from a water molecule and become diol. Do you see that? That's an diol. Once the diol forms, so this is a both carbon has a hydroxyl groups. So we are going to go from aldehyde to a ketone. So the base can grab a hydrogen from any of these. Okay, let's say if it grab a hydrogen from this hydroxyl group, you would end up getting a O negative charge, oxygen negative charge. And then the oxygen, the negatively charged oxygen give its lone pair to form the pi bond, and this pi bond will grab a hydrogen, giving us a ketone. So D-glucose through this diol rearrangement can give us a D-fructose. It's a ketose. So this is a aldose and this is a ketose. Okay. Okay. So these sugars can undergo oxidation reduction reactions. Remember, because it has a carbonyl group. So the reducing agent is a sodium borohydride. So the sodium borohydride reduction will make the carbonyl group an alcohol CH2OH. Okay, so this is D-mannose. Now mannose means when it has a aldehyde group. Right, now you don't have that aldehyde group anymore. Now you have all of these are alcohols, so you don't call it as D-mannose anymore. After carbonyl group undergo reduction, you will call it as an alditol, and this is coming from mannose. You will name it as mannitol, D-mannitol. Okay, it's an alditol. Now let's see if you have a D-fructose. So D-fructose, again you have a carbonyl group. D-fructose, you react with sodium borohydride. Carbonyl group will become alcohol. When it becomes alcohol, we cannot exactly say hydroxyl group goes only one side. There is a 50-50 possibility that you can have the both structures. So when it goes to the left side, that is similar to mannose. Since all of these alcohols, now it is D-mannitol. If the hydroxyl group ends up on the right side, that is coming from glucose, that is similar to glucose molecule, but it's not going to be glucose anymore since you don't have a carbonyl group. So you call it as a glucitol, which is a kind of a alditol. So this is also alditol, this is alditol too. The specific one is mannitol, this is glucitol. And aldose forms one alditol from aldose. From a ketose, so this is a ketose, ketose can form two alditose. It could be mannitol and D-glucitol. Okay. And these sugars can also be oxidized. When it oxidizes, we call those structures as aldonic acid. Aldonic acid. When you reduce, they are called alditols. Now aldonic acid. You can do the oxidation with bromine. Bromine is a red color solution. You put bromine into D-glucose. Okay, so then it would become carbonyl group will oxidize to carboxylic acid. Now it is not glucose anymore. We call it as a D-gluconic acid, which is an aldonic acid. Okay, and then the bromide will generate in the mechanism bromide ions. Bromide ions are colorless. So if the red color bromine become colorless bromide, then we know the oxidation has taken place. Only aldehydes can be oxidized by bromine. Ketones and alcohols cannot be oxidized by bromine. So nothing will happen to these hydroxyl groups. Okay, only the carbonyl group will oxidize to carboxylic acid, which is D-gluconic acid and aldonic acid. Another oxidizing agent is the tolerance reagent. So the tolerant reagent is capable of oxidizing aldehydes and ketones both, meaning aldoses and ketoses. Now this is a ketose. In the presence of hydroxide ion, it can oxidize let's start from here. So this is a ketose here. This will the ketose first will oxidize in the presence of a base to the aldehyde and the aldoses, and then tolerance reagent. Tolerance reagent is silver ions in the presence of ammonia, and then do a base addition that will oxidize all the way to carboxylate ion. And then we will see silver being precipitate as a silver color metal, okay, in this process. So ketoses and aldoses both oxidize all the way to carboxylate ion with a tolerance reagent. So the tolerant reagent is silver ions, ammonia, and a base. Okay. So this carbon will become alcohol, and then the carbon at the end will become carboxylate anion. Ketone first will become an aldehyde, then to the carboxylate ion. Okay. If you use even more powerful oxidizing agent like nitric acid, not only the carbonyl group, but your alcohol, the primary alcohol at the very end, can also be oxidized all the way to carboxylic acid. So this is D-glucose. When you add nitric acid, both carbon, so the aldehyde carbon as well as primary alcohol at the very end, both will be oxidized to carbonic acid, carboxylic acid. We call them as glucaric acid, D-glucaric acid. Their common name is aldaric acid. If it is one, that is gluconic. See, gluconic or aldonic. So this is glucaric or aldaric acid. Nitric acid is a stronger oxidizing agent than bromine. Bromine cannot oxidize these alcohols, but only nitric acid can do. So this Kiliani-Fischer synthesis can increase the carbon chain of an aldose by 1 carbon. How do we do that? By using cyanide. So this is the erythrose, 1, 2, 3, 4 carbons. You react with cyanide. The cyanide group will react with the carbon as a nucleophilic substitution reaction, nucleophilic attack, right? Cyanide group, and then the carbon oxygen bond, pi bond opens up. Okay, and then so this will become an OH group, and then we have added a new cyano group. So when you expand this, so carbon still has the hydrogen, this oxygen will grab a hydrogen and make alcohol, and cyano group will be added on to the carbon. Okay, and in this process you can have the both epimers. So the OH group can be on the right, OH group also can be on the left. So both can be formed with a new asymmetric center. And then when you do the hydrogenation, you do the reduction with hydrogen, palladium and barium sulfate reagent. So this carbon-nitrogen triple bond will end up being a double bond, and then carbon will pick up a hydrogen in the mechanism. Okay, and then when you further react this with hydrochloric acid and water, this would become a carbonyl group. Okay, and at the end you have generated two epimers, D-ribose and D-arabinose, and they are products of C2 epimers. So this carbon hydroxyl groups are differ in their place of attachment, could be right and the left. Kiliani-Fischer synthesis increases the carbon chain of an aldose by 1 carbon, it forms a pair of C2 epimers.